All right, let's dive into a really fun tree problem today. How to turn a regular binary search tree into something called a greater tree. It's a fantastic puzzle, and the solution reveals this super elegant traversal trick that you can use in a ton of other situations. So, here's our game plan. We'll start by figuring out what the challenge actually is, then we'll break down what a greater tree even means. After that, we'll uncover the key insight, this awesome reverse traversal trick, and walk through an example together. Finally, we'll see how that logic turns into code and wrap it all up with the one big thing you should remember.
Okay, first things first, let's get a handle on the greater tree challenge. Before we can even think about a solution, we have to be totally clear on what the goal is and what we're working with.
Just as a super quick refresher, remember we're dealing with a binary search tree, or BST. For any node you pick, everything to its left is smaller and everything to its right is larger. This special ordered structure is the secret weapon we're going to use to solve this. So, this is what we're trying to do. On the left, you've got your standard BST, and on the right, you see what it looks like after we transform it into a greater tree. Just look at the values. They're completely different. The root, which used to be 4, is now 30. The node 6 becomes 21. This isn't just random. There's a very specific rule being applied here, and our job is to figure out what that rule is. To figure out that rule, we really need to deconstruct the goal. Let's just zoom in on what's happening to one single node, and that should help us uncover the logic behind this whole transformation. Let's pick one and see if we can reverse engineer this. How in the world does the node with the value 6 end up becoming 21? There's got to be a calculation happening here. Ah, there it is. The new value for node 6 is its original value, 6, plus the sum of all the values in the entire tree that are greater than it. In this case, that's 7 and 8. So you take 6 plus 7 plus 8, and you get 21. Simple as that. Okay, so now the challenge is clear. For every single node, we need an efficient way to find and add up all the other nodes that have a bigger value. All right, so we know what we need to do, but how? I mean, you could go to every node and for each one search the whole tree again to find all the greater values, but that would be incredibly slow. There has to be a more clever way. And there is. This is where the magic happens, what I like to call the reverse traversal trick. To find this trick, let's ask a slightly different question first. How would you normally visit every single node in a BST? In ascending order, from smallest to largest. If you've played around with trees before, you probably know the answer. You'd use a standard in-order traversal, right? You go all the way to the left, you visit the root node, and then you go all the way to the right. This left, root, right pattern is famous because it naturally gives you all the nodes in a perfectly sorted ascending order. It's a basic, fundamental property of any BST. But here's the twist. Our problem isn't about the smaller values. It's about the sum of the greater values. So to make our calculation work, we really need to deal with the big numbers before we get to the small numbers. So how could we visit the nodes in descending order instead? The answer is so simple, it's beautiful. If left, root, right gives us ascending order, what do you think happens if we just reverse that logic? We do a right, root, left traversal. Instead of going left first, we go right first. By doing that, you guarantee that the very first node you visit is the largest one in the entire tree. Then you'll visit the second largest, and so on, all the way down to the smallest. This is exactly what we need to keep a running sum of all the greater values as we go. Okay, enough theory. Let's put this into practice. We're going to trace our new reverse in-order traversal on that example tree, step by step. And you'll see exactly how this running sum lets us solve the problem so efficiently. So we'll start with a running sum of 0. Following our right, root, left path, the very first node we visit is the absolute largest one, 8. So we add its value to our running sum, which is now 8. Then we update the node's value to be this new sum. Node 8's value becomes 8. Easy enough. Our traversal continues. The next node we visit is the next largest one, which is 7. Our current running sum is 8, so we add 7 to it, and we get 15. We then update node 7's value to 15. And see what just happened? Its new value is its original value, 7, plus the sum of everything greater than it, which was just the 8 we already processed. It works. Let's do just one more to really see the pattern. The next node is 6. Our running sum is sitting at 15. We add 6 to it, and our new sum is 21. So we update node 6's value to 21. And that's it. That's the answer to our original question. This pattern is just so clean because that running sum always holds the total of all the nodes we've visited so far, which by definition are all the nodes greater than the one we're currently on. And this process just continues right on down the line. For node 5, we add it to the sum of 21, and its value becomes 26. This elegant little pattern just repeats for every single node in the tree, and it guarantees that by the time we visit any node, our sum is perfectly preloaded with the total of all the greater values. So the logic is solid, it's clean, it's efficient. Now let's take a look at how this right root left strategy actually translates into code. You might be surprised by how few lines it takes. And that's basically it. This is the heart of a recursive solution. Just these few lines. You'll have a recursive function, often called DFS for depth of first search, and you'll have a sum variable that you keep track of. These simple lines are a perfect implementation of our entire strategy. Let's map it out. That first line, DFS of root.rate, that's our go right first step. The two lines in the middle, where we add to the sum and then update the node's value, well, that's our visit and update the root step. And finally, DFS of root.left is our go left last step. It's a perfect one-to-one translation of our right root left traversal. So after all that, what's the big idea here? What's the main takeaway that you should tuck away in your problem-solving toolkit? Here it is. The real key is that a binary search tree can be traversed in different useful ways. The standard in-order traversal gives you everything sorted smallest to largest. But by just flipping that logic, you get largest to smallest. So anytime you're faced with a BST problem that involves a running total or a cumulative sum of greater values, your brain should immediately go, aha, reverse in-order traversal. And that really leaves us with a final thought to chew on. We solved this entire problem just by taking a standard tool and flipping it on its head. It makes you wonder, right? What other, maybe more complex problems with trees or even other data structures could suddenly become simple if you just